from Dr. Samuel Ting about the AMS experiment and its measurements of the number of electrons and positrons in the universe. And then today, we heard from Dr. George Smoot, who told us that dark matter had to exist from the beginning of the universe in order for the structure and us to exist. Dr. Lawrence Krauss enlightened us about nothing, and sorry, Lawrence, and I'll continue, and how physical laws and space-time could possibly come into existence from nothing, that is. And Father George Coyne helped us explore the difference between creation and origins and the different ways of knowing of science and religion. And we can't forget about the great discussions during the Q&A sessions. I thought there at one point you might have to get the fire hose out. And of course, we are excited to hear what Dr. Jim Gates will have to say this evening and about how we test scientific ideas. It has been an awesome 2 days. I hope you had as much fun as I did. I know that I'm tired, but I also know that I'm not alone. Putting on a conference of this magnitude is a community effort, from the electricians, plumbers, and carpenters helping direct traffic, to the students ushering, serving our food, and playing the prelude music. We can't forget the faculty who organized and hosted and directed the concerts. Without everyone's help, this conference wouldn't be possible. At the same time, I need to mention a few groups in particular: the folks in dining service, marketing and communication, media services, and heroic productions. Let's give them a round of applause to show our appreciation. And of course, we need to thank all of our speakers. Let's give them one more round of applause. At this time, I'd like to introduce my good friend and colleague, Dr. Steve Melma, to introduce our last speaker, Dr. Jim Gates.
Thank you, Chuck. In 28 years on the faculty at Gustavus, this is the first time I've ever been the chair of a Nobel Conference. And I've hosted before, but it's my first opportunity to chair, and I didn't know what that entailed. And as I was having my dinner tonight, I realized that the chair never had an opportunity to speak, especially with those guys in the Q&A. Now, what I wanted to do is simply add my thanks to Chuck's thanks to our wonderful speakers, not just for their fabulous talks, but for what's been really meaningful to me as a teacher, to watch the fellowship that they have given to our student hosts and our faculty hosts. To watch that dynamic occur behind the scene is priceless. So thank you for that as well. Well, now to the topic of the evening. What really is in there, inside all the stuff that makes up our universe? If we try to reduce things to their smallest, most fundamental parts, how far can we go? The ancient Greeks thought that atoms were indivisible, but by 1932 we had experimental evidence of 3 subatomic particles: protons, neutrons, and electrons. By the end of the 20th century, we had experimental evidence of almost 200 different types of subatomic particles, a veritable zoo of them, created in the ways that you've heard about in the past 2 days. Some have been forged in the great accelerator laboratories around the world. Some arrive at Earth from cosmic events elsewhere in the universe. You've learned during the course of this conference about the Standard Model, which says that all of these various particles can be made up of just a small number of constituent parts, 6 quarks and 6 leptons, with a few gauge bosons around to mitigate the forces between them. But can we ask the next set of questions? Have we found all of the particles that exist, or are there more to discover? Is there something even more fundamental beneath the level of quarks, leptons, and bosons? It is my honor and pleasure this evening to introduce the final speaker at the 49th Annual Nobel Conference, The Universe at Its Limits. Dr. Sylvester James Gates, Jr. is University System of Maryland Regents Professor, John S. Toll Professor of Physics, and Center for String and Particle Theory Director at the University of Maryland. Jim is a mathematical physicist whose work involves probing the mathematics and symmetries that underlie the most fundamental things, that is, the energy and the particles, which make up our universe. This work has led him to the area of string theory and the idea of superstrings, unimaginably small entities which vibrate or rotate in multiple dimensions and which, taken together, may explain all of the matter and the forces that govern our universe, including the holy grail of theoretical physics, a consistent quantum theory of gravity. In doing so, the theory predicts the existence of an entire set of superpartner particles to accompany the particles that we have already discovered thanks to the predictions of the Standard Model. Professor Gates received all of his degrees, both undergraduate and graduate, from MIT. His Ph.D. thesis in 1977 was the first thesis ever published there on this idea of supersymmetry. He went on to do postdoctoral work at both Harvard and Caltech, and then he joined the faculty at the University of Maryland in 1984. Jim has published books, chapters in books, and dozens of scientific papers on the theory of what may be the ultimate constituents of our universe. His work, both in mathematical physics and as a teacher and communicator of science, has led to international recognition and to numerous awards. He holds honorary degrees from the University of Western Australia, Loyola University Chicago, and Georgetown University. He's been elected to membership in the American Academy of Arts and Sciences, the American Philosophical Society, and the National Academy of Sciences. Earlier this year at a White House ceremony, he received the National Medal of Science from President Obama. And he's told me that after the president's term is over, Jim can tell you the joke that he told him that elicited this laugh, but not till then. This year, 2013, he also received the Mendel Medal from Villanova University, and I quote, for his groundbreaking work in supersymmetry, supergravity, and string theory, as well as his advocacy for science and science education. Jim is very actively involved in science policy discussions, and since 2009, he's been a member of the President's Council of Advisors on Science and Technology. He's also a science educator and a person who, from my own experience, I know to embody the finest traditions of the liberal arts. In 2005, we were fortunate enough to have Jim as one of the speakers at Nobel Conference 41, commemorating the work of Albert Einstein on the centennial of Einstein's miraculous year. And 2 years later, Jim graciously agreed to come back to Gustavus under the auspices of our Rydell Visiting Professorship. I had the personal experience of a lifetime by team teaching with him a semester-long course on string theory, but a course we created specifically for a general non-scientist student audience. Through that experience, I have come to know him as both a brilliant scientist and a superb communicator of science to a general audience. I think perhaps that the best introduction you could have to Professor Gates is the citation that went along with his National Medal of Science, which you see here. It reads as follows: for contributions to the mathematics of supersymmetry in particle, field, and string theories, and extraordinary efforts to engage the public on the beauty and wonder of fundamental physics. We are absolutely delighted that again this year, Jim has agreed to serve as our Rydell Visiting Professor, and that he has agreed to give the final talk of this 49th Nobel Conference. The title of his talk this evening is The Audience of Nature. Please welcome Professor Jim Gates.
Wow. What do you say after an introduction like that? Well, first of all, I obviously would like to thank Jack and Chris and all of my friends here at Gustavus, all my friends here in St. Peter. I actually love this campus. This is, 20th visit? It depends on how you count. I get back here as often as I can and as often as I'm invited to. After our first experience here at the Nobel Conference, that summer I brought my family here. We enjoyed St. Peter so much. We spent about 2 weeks here and went sailing with Chuck and just had a great time. So it's truly the case that when I come to this campus, I feel like I'm returning home. It's a very odd thing, but true. Well, I recognize that I'm the last thing between you and your exit. So so the onus is on me to get this done, get it done in an enjoyable manner, and let you get on with your life. Let me also thank Steve for that introduction. It was a little bit longer than I like, but not too long. I do a lot of speaking like all of our guest speakers, and let me just give tribute to all of these folks. I mean, from Tara to Frank, to George, Alec, where are you? That guy I taught general relativity to many years ago, Krauss, I think his name was. He reminded me as we were coming off the stage today, he said, you know, you're the first person to actually talk to me about general relativity. And I took away from that, you really need to be careful who you talk to. So that, as I said, that introduction wasn't too bad. But oftentimes when I speak these days, I have a document I send where people can draw material out for an introduction. And I'm sure some of our guests have had the same experience. You send a document, you say, pick out just a few things, and your hosts don't get that part of the message, and they try to read the entire document, and it goes on and on. So one such occasion, I was with a friend sitting next to me, and the person doing the introduction just went on forever. And my friend at some point leaned over and said, you know, Jim, we've all heard of a man that needs no introduction. And then he said, but that's an introduction that needs no man. So as I said, let me try to get through this. I'm going to be paying tribute to the people who have led me. As I said, some of these people were just heroes of mine, and the Right Reverend Krauss was just fantastic. Where's George Corn? George, watching the byplay between those two, it's like, there's this African aphorism that the ants need to stay out of the way when the elephants are stomping the grass. And watching those two guys, it's like you just want to make sure you don't get between the two of them. Lawrence knew I was going to do this because he ragged on me today several times, and so we kind of traded. So let me get started. Dimensions. This is something that Frank talked about, something you hear about. And it turns out that for those of us who work on these kinds of things with dimensions, oftentimes people wonder, well, how can you see those things? How can you see these extra dimensions? And in fact, the answer is we don't see them any more than you do. We just have this weird sixth sense. It's called mathematics. In fact, the way that theoretical physicists use mathematics is as a sensory perception organ. And so when we're talking about extra dimensions, we're talking about the mathematics and what that allows us to view. Now, these images that you see running here are, in fact, a tesseract. What's a tesseract? Well, if you take a square and lift it vertically, you get a cube. If there were one more direction and you lifted it in that other direction, this is the object that you would see. Now, of course, there is no extra fourth dimension aside from time in which we can lift such an object. So instead of actually being able to see it, we can draw its projection. And so just like we draw a cube on a sheet of paper, you say it's a three-dimensional cube and you're used to looking at it, this is a four-dimensional cube projected onto a two-plane. And this is what it looks like. And the motion here is actually we're rotating it around one of the directions. And that's why you see this funny motion. So that's how we see extra dimensions. It's with mathematics. Now, I'm not the first person to make this observation about the power of mathematics. There's a wonderful quote by, getting old here, folks, by Darwin, who said something like, with mathematics, it is as if one is endowed with a new sense. And this is the sense that he's talking about. So my talk is really going to be about what people from my end and Lawrence's end, what we kind of do in trying to make a contribution to physics. I have the greatest admiration for Tara and for George, because those folks actually go out and do the things that allow us the freedom to think about this. I'm often known for saying that physics is not a faith-based endeavor. And the only reason that is true, and I should have mentioned Alex, the only reason it's true is because our colleagues go out and build devices that go out and look at the universe, that bring us information that we can then use in our deliberations. And that's the source. That's what distinguishes theoretical physics from something else. Now, unfortunately, our public in general doesn't really understand this. So I'm sure Frank has had the experience. I'm sure George has had experience. I know Alex has had this experience, and Lawrence, and maybe even their father Coyne, I don't know. But when you appear in the media talking about science, something like this, the general public assumes that whatever you're doing, they can do too. And so in my case, one such example was a young man sent me a letter. It was after The Elegant Universe had been broadcast initially back in the mid-90s, mid to late 90s. And this letter came from England. And the first line of the letter is, "Urgent, Professor Gates needs to read this." So I opened the letter up. And the young man, the letter starts, "Professor Gates, I saw you on The Elegant Universe. I'm sure I can help your physics community get to the next level." And I read a little bit further. He says, "Those extra dimensions that you folks are having such difficulty dealing with, I know exactly why they're there." You read down a line, and I'm not making this part up, folks. He said, "Those extra dimensions are where the dead live." And as I said, I'm sure that every one of my colleagues here has a story like this. And so, as we theoretical physicists talk about science, as has gone on this conference, the great danger is that we as a society do not have the kind of appreciation for what science is. And so what is actually science? Well, I like to say it's the way that we achieve the deepest knowledge about the place where we live when we're not there. Because science really is like studying a house. When the occupants are gone, you want to know how the light switches work, you want to know how the AC works. That's what we're doing with the universe. And these wonderful discoveries, whether they range from QCD to back to the near beginning of the universe, it's all about studying the house. And so one of the things about the kind of physics that we theorists do, I like people to know that, it's not that even though people talk about a theory of everything, I'm not sure how many physicists actually take that expression seriously. Or when you hear about the God particle, right? That has been something much in the media for the last few years. How many physicists take that seriously? In fact, there's a story about that is well known to people in the physics field, and most of you are not physicists. So where did that name come from? Well, Leon Lederman, who is the former director of the Fermi Tevatron Laboratory, has a very salty mouth. And supposedly, one day he was overheard to say, "Where is that God blank particle going to be found?" And I don't have to fill in the blank. Right? So this gets into the media, and then suddenly it becomes shortened to the God particle. Right? So that's the kind of thing that goes on in our community. So what I'm going to do today to try to get through this is I'm going to pay some tribute to what's going on. For people like me, this is how we see the world. Please don't take out your crosses and start throwing holy water, because it's not going to hurt. We're going to have just a little bit of this math stuff. But for people like me, this is how the world looks. We use mathematics to actually see the world. In fact, one question I often like to ask people is, how big is an atom? And scientists know how to answer this question, but if you talk to most people in our society, they cannot answer the question, how big is an atom? So there's a story that I like to tell people. Take a yardstick, break it up into 10 equal pieces, throw away 9. You go from something this big to about something that big. Take that remaining object, break it up into 10 equal pieces, throw away 9, get to something about the size of the width of my fingernail. How many times do you have to do that to get to the size of the atom? Answer turns out to be only 10 times. And yet, atoms and atomic energy, I mean, this is one of the most widely discussed subjects in our society, but almost nobody knows the size of an atom. You can even ask the question, who was the first person to know the size of an atom? And the answer is rather interesting. It's this guy named Albert Einstein. In the same year that he invented special relativity, he also did a very famous paper on what's called the photoelectric effect. Capillary motion, Brownian motion. And in that paper, he was able to use mathematics to figure out the size of an atom. So he's the first person to know the size of an atom. So this is what the world looks like. And what I've done here is I've actually written some expressions. If I could prepare beams in an idealized world, the first one is a beam of Higgs particles. Math looks like that. It's got some trig functions in it. So, you got to make your peace with trig if you're going to try to do this stuff. If I made a beam of electrons, the form looks like this. And if I made a beam of photons, it looks like this last arithmetic expression. Now, there's something rather interesting about these expressions. You'll see this one has this crazy term, phi over 2. This has this quantity phi. It turns out that the spin, and we're going to be returning to spin later. So what I've done here is I've written expressions for these beams moving along using what's called cylindrical coordinates. And when you do that, you find out that what's called the azimuthal angle shows up with a number in front of it. And that number turns out to be the spin of the object, classically. So the first one there, you see there's no phi. The Higgs particle has no spin. The second number is a half. The electron has half a unit spin. The photon has a full 1 unit of spin. Now, what's this math good for? Well, one thing is you get really weird pictures. You see, that last expression that I wrote for you for the photon, if you actually sort of turn it over to a computer and do some graphics, you can get an image like this. It looks like a hopscotch game of rings and stars as they move along, and that represents the propagating photon. Now, is this good for something? Well, not really. I just did this to waste your time. But it does show you the power of mathematics to visualize the world in ways that you had not thought about before. And that's the power that we use in order to accomplish our goals. Let me bring this a little bit more quickly to supersymmetry. Many of us have seen table of elements, but when Mendeleev initially found the table of elements, this is how it looked. You see all those blank spaces there? Well, because those spaces were there, he suspected there had to be other elements in nature that no one had ever measured in the laboratory. And in fact, subsequent to writing this table, those elements were found until we get our modern version of the table of elements. Now notice, this doesn't look like mathematics, right? I mean, we went from one chart to a more complicated chart. But in fact, there's a sense of mathematics. It turns out mathematics is not only done with equations. That's one thing to understand about mathematics, that we actually do mathematics in many ways. And in fact, one of the things that is on the horizon about mathematics are things like this, computers. A large effort is underway to use computers to visualize data. And in fact, we saw a great example of that in a number of the presentations, especially the one with George, where he showed the distribution of the dark matter as we looked back towards the formation of the structures in our universe. And so the kind of visualization you do with computers actually gives you another road to mathematics. Now, this is actually something very different, something, as far as I can tell, has not existed for our species before. There's a very famous saying that there's no royal road to geometry, which maybe some of you have heard. Supposedly, Archimedes, I believe, was supposed to be tutoring some ancient king, and the king said, well, gee, why do I have to do all this stuff like the commoners? I mean, can't you do something special for me so I can learn the geometry? And the response was, there's no royal road to geometry. Well, there may be an app. There may actually be an app. If you stop and think about it, what computers actually, one way to think about a computer is that it is the equivalent of a musical instrument, but it does this for mathematics. Computers are kind of made to play mathematics. Now, I don't know what this is going to do for our species, but I have some very strong suspicions that over the long term, as we become more familiar with using computers as a way to access mathematics, that you might have in mathematics something that occurs in music. There are musical geniuses that don't read scales, but are extremely accomplished people. One can imagine that with a sufficiently long time of technology, exposure to this technology, we humans will find another way. That's why I said there might actually be an app to geometry out there in the future. And in fact, there are a lot of people working on this. This may have an enormous impact on one of the problems that we have in this country, namely STEM education. In my capacities of advising both the White House and being on the Maryland State Board of Education, this is one thing I worry about enormously. And there are, in fact, commercial entities right now trying to develop apps that will allow students in middle school and in elementary school to learn mathematics in a way that those of us my age never thought about. And so we may be on the precipice of something entirely new in terms of how we as a species engage mathematics. When I started grad school, this was what the standard model looked like. We knew about the electron and the muon, their associated neutrinos, the up and down quark, the strange quark, and the photon. There was a fantastically successful theory telling us how photons interacted with electrons called quantum electrodynamics, which we actually have heard talk about. And then Frank showed up. The Frankon was discovered. Frank, David Politzer and David Gross, around 1973, lifted a veil on part of the way the universe works by showing that there were a set of equations that had actually been around in principle since around 1954. They're called the Yang-Mills equations, but they had the intuition of how you could use these equations to predict something about nature. And this shows something also about mathematics that people generally don't appreciate. I like to ask people, next week, do you think there's going to be more music than there is now? Right? Next week, is there going to be more mathematics than there is now? The answer turns out to be yes. Now that stuns people often, because oftentimes, because of the way our education works, people think mathematics is this rigid, fixed thing, kind of like history, right? You can't go back and change history. Once you've learned history, it's going to be fixed. But mathematics, in fact, is more like music. Mathematics is actually created. And in fact, I have a very great suspicion that the creation of mathematics works rather similar to the creation of music. In fact, psychologists have long known that there are, in fact, correlations between musical ability and mathematics ability. So that also has very interesting implications as we think about the diversity in our society. Because if it's true that mathematics is as close to music as some of us suspect it is, that means that in mathematics, the notion of style can exist. Again, something rather strange to think about. In fact, I know many colleagues, and when I say this, they say, Jim, you've gone right off the edge. How can style exist in mathematics? Well, my response is go back and read the mathematics literature of about 100 years ago. If you don't think that's a different style than what we do now, then you're not paying attention. That means in particular that as we think about our society becoming more capable to deal with the innovation and entrepreneurial environment in which we Americans will exist, and therefore we struggle to get our general population educated and capable to deal successfully with some higher level of mathematics. It means that this issue of style may become crucially more important. Now, I don't quite know how to take advantage of this, but I'm absolutely convinced that this is something that we as a democracy are going to have to address. So after Frank, we got this. This is sort of more Frank and his equations. Well, that looks boring. Remember I told you that, in fact, mathematics is dynamical? Well, here we go. This is a little cartoon that tries to illustrate what Frank and David and the other David tell us about trying to actually they did it in reverse, how the force between quarks behaves when they are very close. It turns out they act like they're almost free particles. But when you try to separate them, it is as if you have rubber bands attached to them. And it becomes harder and harder to pull them apart. In fact, it becomes so hard that you can't actually pull them apart without the energy in the rubber band converting itself into a quark-antiquark pair and getting new hadrons out. Now I'm going to skip ahead here because I wanted to, since I'm on Frank at this point, I want to show something else Frank did. Frank alluded to this in his talk, but I'm going to be a little bit more explicit about it. You see, we live in a very strange world, and one of the things about our world is that the forces actually change their behavior depending on the strength at which you look at them. That is, the higher the energy that you look at them, the different it is as if you imagine an electron, the two electrons repelling each other, the strength with which they repel each other depends on the energy at which you investigate the question. And Frank and David were the first people to point out that the equations that they found have the properties. So this pink line here is the strength of the force between quarks. They're the first people to find that there's a force in nature that has this kind of behavior that as you go to higher and higher energies, you get a dropping in the amount of repulsion effectively between the quarks. This is, in fact, was the origin of the Nobel Prize that David secured that Frank secured with the two Davids. So Sam was the next person who showed up in my life. I was a graduate student at MIT, actually, when Sam Ting did his work, which led to the discovery of the J. And I actually remember one of his research staff was actually a teacher of mine at the time. And one day this gentleman, whose name is lost to my memory of times, came running into the class excited, saying, "We have found a new particle." Now, this is MIT, right? A lot of bright people, all the kids, all of us students sitting there, and we're like, duh. What does that mean, new particle? And then it was explained to us that there were scattering amplitudes that showed that a quark that had actually been theorized before, and this is once again to understand how mathematics interacts with science, the thing that they had found in the laboratory had actually been theorized before it was found, like a lot of the things that happen in physics. And then we get to the modern version of the Standard Model. And that tells us where we are right now in terms of our understanding of very small things. Well, there's this guy named Einstein that intruded in my life. Let me say this two ways. I first met Albert Einstein when I was 16 years old. Let me make sure you understand that I did not literally meet Einstein when I was 16 years old. I emphasize the second because once a reporter heard the first quote and wrote a story saying he got interested in science when he was 16 and met Albert Einstein. So you have to be very, very careful when you speak to the media. We had a wonderful discussion earlier today about the possibilities, both in Alex's presentation as well as George's, about Einstein's, what he called the biggest blunder. He wrote this equation which actually had 5 different ways the universe could have gone. What we see on top is if this thing called the cosmological constant 0, you can get a universe that explodes into existence. If more of the energy is in the matter than the gravitational field, it expands forever. On the other hand, if more of the energy had been in the gravitational field than in matter, you get an explosion followed by a big crunch, something we've heard about today, crunches. But Einstein thought the universe was static and eternal, so he used this constant to fix a bubble in space. That's one way to think about it, that the universe was just this bubble, it didn't change. And later Hummerson and Hubble came along and said the universe is expanding, and at which point he said, gee, I've got to erase this term. I like to say Einstein would have been a great physics student. Why do I say that? Well, many times, if you're a physics professor and you give students a laboratory assignment or a piece of homework, but let's say a laboratory assignment especially, ask them to write a laboratory report, they'll give you the result that everyone knows is the right answer. But if you dig down into the laboratory report, you'll find that someplace in the report they have learned to use an extremely sophisticated piece of mathematics called the fudge factor. Einstein knew how to use fudge factors. And effectively, that's what the cosmological constant was. Now, as was mentioned today in Getting the Universe for Free, we actually make use of this cosmological constant, but in a way different from Einstein. Because you see, Einstein initially wanted this fixed bubble that we see here. But in fact, the cosmological constant, which we now think is present, has the sign that is different. It's not only the size. I mean, we heard, I've forgotten which talk, but we saw this talk with, I think it was Lawrence's talk with all these zeros stretched out, right? That's the size of what you might predict, but it turns out it's not that. But it's got the wrong sign even from the initial cosmological constant that Einstein wanted to use to hold the universe fixed. During Father Coyne's presentation, and also during one of the others, we heard about Lemaitre. I think that this is something we scientists really need to celebrate. That in fact it was a person of faith who actually started the idea of a Big Bang. Now I think that's a really important thing to say in this country because there are elected officials in this country who believe things like the Big Bang and evolution came from a very hot region under our feet. And it's important to get the message out that no, someone of faith started this idea, a Jesuit priest, or as Father Coyne said, someone who was accused of being such, started this idea. And one of the things that I think is really important, as we had this big debate today, I think in fact it is critical that those of us on the scientific side of the argument make space for people to maintain their faith. And that we, I don't believe, are in position even to attack faith. Now, my friend Lawrence might disagree with me, probably does, but from my perspective, I don't actually understand how science can actually attack faith. And it has something to do with a tradition started with St. Augustine, but popularized most recently in our society by Stephen Jay Gould, who had this idea of the non-overlapping magisteria. He said that religion and science are separate magisteria and they don't overlap. Now, you don't have to accept that, but you know, I'm a scientist, so when people tell me something like that, I actually start looking for mechanisms. Because in fact, it goes back to the statement that we heard in the presentation. Often the question is why, when the question should be how. And so I've actually been thinking about a mechanism by which this could be achieved, that they're non-overlapping magisteria, but there's a mechanism at work. And I think I kind of know what the mechanism is. Now, I haven't written this up, and I will be challenged to do so in about a month, but I'm going to share my thoughts with you, and you can shoot me down, especially Lawrence. I'm waiting for you to pull out your weaponry. But as I understand how science works, science is not just telling a story, item number one. When we say something that's a scientific result, it's not that we're just telling you a story. We also tell you how to verify that our story is accurate. That's actually very unusual. Because if you look at most of the sense-making that we humans do, we make up stories, we make up scenarios to explain what we see around us, but almost never is the scenario accompanied by a way to verify. You remember that statement that Ronald Reagan was famous for? Trust but verify? Science raises that to a principle. We make statements, but we also tell you how to verify the statements. Now, if we turn this argument a little bit further, one of the most extreme, perhaps, expressions of religious belief is a belief in miracles. And so, can science even see miracles? I'm not sure it can. Why not? Well, let's imagine that I performed a miracle. And in fact, let's even go further. Let me announce to my friends in my physics department that tomorrow I'm going to perform a miracle. Now, most of them will say, well, Jim's been on the road too much, or else he's gotten some bad drinks or, whatever it is, and they would simply ignore me. But if I could convince a few friends that I wasn't totally insane, then maybe they would say, okay, well, Jim, why do you think you're going to perform a miracle? And I said, well, I'll perform it here. And if I really had some really close friends, maybe they would even instrument the spot where I performed the miracle. Let's imagine all this happened. And when the time came, let's also imagine that I actually did it. So there would be this report. Jim Gates performs a miracle. Here's the documentation. We instrumented this region. This was the phenomena. This is what we saw. Is that science? Is that scientifically credible? The answer turns out to be no. In fact, we have examples like this in science. Many years ago, it was reported that a magnetic monopole had been seen by Calabrese at Stanford, Cabrera at Stanford. You can read the literature. There's reports. Monopole seen, magnetic monopole seen. No one has ever seen it again. And so even if I performed this alleged miracle and there were scientists to record what happened, it would in fact not be scientifically credible. For the very simple reason that when we say something happens in science, you've got to be able to convince yourself that it occurred. So you might say, well, Jim, you could perform the miracle the next day in the same place. Well, yeah, that's true. Maybe I could if in this hypothetical situation where I had these godlike powers. Yeah, sure. But at some point, I'm probably going to die. And then 200 or 300 years in the future, people, again, who are scientists say, what scientific piece of evidence, what can we do to convince ourselves that this occurred? And I don't see anything that you could do. And therefore, I don't see how the alleged miracle could actually be seen by science. Now, there may be holes in this argument someplace, but I think that's the actual mechanism by which science and faith, if you think of faith as being manifested in miracles, I think there's an actual mechanism that stops the two from colliding. Because science is set up in a way that it's got to be reproducible by anyone at any time in any place. And if you can't satisfy those conditions, you cannot maintain scientific credibility. So I think it's a very simple mechanism. Like I said, I'm willing to engage others like my friend Lawrence, and maybe we'll come to something better and he'll shoot me down. So as I look at the world, I think that for most humans, science and faith should not be viewed as, in fact, I think it was Frank who used the word complementarity. I think that's the right way to think about it. That the two are complementary, that the two, in fact, don't actually overlap. That there are different ways in which the majority of our species will choose to look at its experience in reality. I like to say that if a loved one of yours was in an accident and you suddenly got a report, you'd probably do two things. You'd reach for your mobile phone to get the information, and you might say a little prayer. That's how most people act. Now, maybe we scientists don't act that way, but that's how most people act. And I don't see that it is destructive to say that they shouldn't have such beliefs. So back to our scientific story, Lemaitre established the idea of black holes. Einstein's general relativity starts to let us see all sorts of phenomena in the universe, such as how to understand the explosion of stars. This is a very famous online representation of a supernova called Eta Catenae. The statement by Carl Sagan that we're all made of star stuff is based on this. To me, this is one of the greatest poetic statements in science I have ever heard. That we are all made of star stuff. That we are all connected to the stars up there in a way that without science you can't even know about. And this again shows the value of science as a cultural lever. It's not just about knowing the facts. It's about establishing a mindset of your relationship to the entire universe. That's something very different from most ways of making sense of the universe. Dark matter, which we heard about brilliantly described to us by George, goes back to the Fritz Zwicky, as we saw with the funny pointing finger. Not necessarily the most popular person. Vera Rubin, about 15 or 20 years later, found the same result looking at galaxy rotation curves, which we actually see in this transparency. And also, as George said, although I must admit I hadn't paid enough attention to pick this out before, I have an animation here running of how galaxies evolve both with and without dark matter. And what you'll find is that without dark matter, galaxies fall apart too soon. They don't exist on the time scales that our galaxies exist. So we needed dark matter to stabilize galaxies. But George Smoot, in his presentation today, taught us that you need dark matter even to form the galaxies in the first place. So dark matter is not an afterthought. It is an essential part of how you build a universe where creatures like us can reside comfortably. This is something called a Holmdel horn. This, again, touches on Arnold, Penzias, and Wilson. This is one of my favorite stories, that after they cleaned the pigeon droppings out of this thing, they became convinced they were receiving a signal from outer space. Those days it was called a 3-degree radiation. I remember hearing about it as a kid, wondering what in the world were people know. I mean, were nuclear bombs going off out there, right? Because radiation, remember I was born in 1950, so when we heard the words radiation, it was either mutants or nuclear weapons, right? So I was a puzzled graduate student, and I couldn't figure out what to study. There were two things I wanted to graduate school. One of them was particle physics, and the other was relativity and cosmology. Those are the choices I had to make as a graduate student. The reason I chose particle physics was data, and not the character on Next Generation. Data. Data is what drives science. And as I viewed from my immature, and I agree, I was young graduate student, not really well trained, but to my intuition, if you give me two options, one where there's a surfeit of data and another where the data is much, much less, I would say the better chances of doing science is to go with the data. And that's what I chose. That's what cosmology and astrophysics looked like to me back in those days. This is probably the worst science fiction movie of all time. I see some heads shaking yes, so they know this movie. Avoid this thing like the plague. If you ever hear of Plan 9 from outer space, don't watch it. So here comes George to straighten things out again. In 1992, with the Kobe experiment, there was an enormous increase in our understanding of the 3-degree radiation in terms of the inhomogeneous nature of how it was distributed. And then finally, of course, we have had a series, and today we heard a great explanation on what Planck is doing to us and the precision that the data, and did you hear the word data? The precision that the data is bringing to us in trying to formulate our pictures of how the universe works. This is the cosmic microwave background. When I talk to the public, and I kind of consider you folks kind of family, so you're no longer the public to me. But when I talk to the public, I love to put this in front of people because I say, there are not a lot of people who argue whether dinosaurs existed presently. And part of the reason for that is because a lot of people can go to a museum and see dinosaur fossils. There are a lot of people in our society, when you say Big Bang, which is why I asked the question to George today, is how do people react when you start telling these stories? But there are a lot of people in our society that if you say Big Bang, they'll ask you if you're talking about the TV show that George was on. But then, if you say, no, not the TV show, we're talking about science here, they'll say, oh, you're out to undermine my faith. We see this a lot in this country. I like to tell people, no, do you believe in dinosaurs? And most people's faith, by the way, no longer contest the existence of dinosaurs. There was a time when they did. They don't now. Well, I like to say there's a fossil in the sky that you should learn about, which informs us why we believe in the Big Bang. And notice the word believe, because actually that's a misstatement. We don't believe in science. You see, belief is wishy-washy. We have evidence for. When people ask, and in fact, that's one of the things that if you're a scientist or someone who supports science and someone says, do you believe? That's the wrong question. The question is, do I have evidence for it? And whenever that question is put to me, I always try to remember to correct the questioner. It's not a matter of belief. It's a matter of evidence. And I think that precision of speech is something that I think that those of us who support science need to be very careful. Do not fall into the hole of having someone ask you, do you believe in? The question is, do you have evidence for? So here's some more dark matter. This is something called the bullet galaxy, which is great. It was a collision of two clusters, actually. And what it shows, again, similar to something that was discussed today, that you can look at the starlight behind it, and the greatest maximum bending occurs where the matter ain't. It's where the dark matter is. We have this energy distribution. It looks something like this. And again, we learned that gravity is a lens, and we heard a beautiful explanation today from Dr. Krauss on how, using the size of the spots in the cosmic microwave background, we can figure out things about the omega that's associated with matter. The subtlety of this reasoning is something that, this is not something that, one of the great things that I have to tell you, one of the great things about this conference, I think this is the biggest conference I have ever seen where this precision level of cosmology has been talked about for non-scientists. I've never seen a group that's been sort of presented, and it's been presented in an acceptable way by all of our colleagues who gave the lectures, and I think that's actually something very special. So you all actually deserve to give yourselves a round of applause, because you folks have now been initiated. You now know why scientists make these kinds of statements at a level that almost nobody in our public does. It's like the question about the atom that I asked you earlier. Almost nobody in the public knows how big an atom is. Well, if you remember my story, you now know how big an atom is. And from this conference, you now know more about why modern cosmology is a precision scientist. It has this thing we call the standard model, lambda CDM, lambda for the cosmological constant, cold dark matter. Lambda CDM is the acronym. You now know why scientists with ever increasing assurance say this is the universe in which we live. So this is what we went through. We didn't talk so much at this conference about gravity waves, but that's one of my favorites. This is an animation of neutron stars generating waves of gravity. going out from the binary neutron star system, going out through space, and eventually they would come down to the planet Earth, we hope, if we're lucky. You spent about $600 million at this point looking for these things. You do it through your tax dollars. There's two facilities called LIGO, the Gravitational Wave Laser Interferometry Gravitational Wave Observatory, located in two places, Washington State, Hanford Reservation, Louisiana, north and west of New Orleans. Those are the sites. That's what it looks like. You Americans have invested, as I said, about $600 million so far and counting to build these facilities, to look for these waves of gravity. Now, as emphasized in both Dr. Krause's talk and Dr. Smoot's talk, if we ever get these waves of gravity, it's going to allow us to look behind the curtain that's represented by the cosmic microwave background. We will be able to see even closer to the Big Bang if we are able to detect these gravity waves. Dr. Ting showed us this marvelous thing about antimatter, and in this cartoon here, the big takeaway of it is that these things at the bottom are these things of dark matter that we really can't see, but mathematically we can sort of describe their behavior. The two dots that you see coming out of the other side represent the positron and the electron, and those are the things that we're looking for in his experiment on Space Station Freedom. If I return to the microcosm where people like me kind of live, it kind of looks like this. This is what's called a Feynman diagram. That's what we call classical physics, this very simple Feynman diagram. However, the quantum world, which you keep hearing these words quantum, is a much more complicated place. We have diagrams to represent the way the forces behave, which you can see in these pictures, and these additional diagrams slightly modify the forces. Now, a lot of people have trouble with quantum mechanics. They say, gee, you know, you guys talk about electrons walking through, people walking through walls and all kinds of strange quantum effects where things come into existence and disappear. That can't be our reality. I like to tell people, if you don't believe that, take this off. It is loaded with quantum mechanics. You should remove your mobile phone because it works on the principles of quantum mechanics. So if you have difficulty believing that, then why use this thing? We talked about with Tara, the Large Hadron Collider. And this is a cartoon that I had commissioned. I'm sorry, I apologize for not including LHCb, but we just put the big cartoon versions of the CMS and Atlas detectors. As Tara said, you ride in this pipe and tens of millions of protons go past you. And then we have these big iPhones. Well, we call them detectors. The big iPhones. They take the pictures, and although the picture that Tara showed you was the way that the computer simulations say the data work, this is what you can take poetic license and imagine. That there's some big imagined puff in there that you've never seen the likes before. That allows us, so here's the computer simulation, which is more accurate. That allows us to do some things like explain how radioactivity works. Radioactivity is actually very interesting. If you put too many protons together in the center of a nucleus, they tend to actually fall apart. Now what's really interesting is they don't do that all the time. If you take two hydrogen atoms and put them together, the thing that you get after it's actually more stable than the two separate. That's why the sun burns hydrogen to helium, because it's getting to a more stable state, actually deuterium. But if you keep doing this all the way up to iron and keep putting protons together, then you find out it becomes easier to take the nucleus apart. Again, a lesson that and when you try to explain this, you need something like massive, weak vector bosons. They're things that are like photons, but they communicate the weak nuclear force, but they have to be massive. And that's what the Higgs particle is all about. I like to use this word, this strange word that Sir Peter Higgs invented. Anderson, Brow, Engler, Guralnick, Higgs, Hagen, Kibble, and Tuft. Now, I don't know how to pronounce this word, but it's an acronym for the last names, but these are all the people who actually contributed to the notion of the Higgs particle. What it represents mathematically is a story. In fact, I like to tell people that, as a theorist, what I really do is I use math to tell stories. That's all. My wife likes to say I make up stuff. But what I'm really doing is what a novelist does. I use mathematics and I tell stories. The story we just saw here of this object rolling down the top of a hill, giving mass to the things at the bottom, which represent the photons, as well as the weak force carriers, that's what the Higgs mechanism is about. It's a story. It's a story about something that rolls down a hill. Last July, we actually saw the Higgs for the first time. So what I've tried to do is first salute my colleagues who have given you all of these amazing stories of science in this conference. They've initiated you to a level of detail that most people will never see in their lives about understanding the way that our universe is put together. And I want to end by going to two things. One of them is supersymmetry. So I'm going to do that in a few slides, and then we're going to stop, and I'm going to let you go. In this transparency here, there it goes, what I've represented are two bosons, or two particles, and we're going to give them the name bosons. Whoops, it looks like I don't have the repeat on. Let me try this again. And these two particles on the left-hand side have charge, but on the right-hand side I turned the charge off, and if you looked at the picture, what happens, they went right through each other. Particles of light do that, by the way. If you take two flashlights, aim them at right angles to each other, the beams go right through, particles of light go right through each other. If you take two electrons and try this, you find out with charge, the electrical repulsion repels them, scatters them. But even if they don't have charge, let me do this again, look to the right, you still get repulsion. There's something called the exchange force, which all fermions have. Even if you turn off all the charges on them, they repel each other. That's a simple definition of what's a boson and fermion. Bosons are things that when you turn off charge, they'll pass through each other. Fermions are things turn off all charges, they still will not pass through each other if they're identical. So the world that we live in has two parts, bosons and fermions. So if you look at the standard model, it actually looks like this. All the matter are fermions. All the force carriers are bosons. And now I ask you, even as a non-scientist, does that picture look balanced to you? Right? Not really. So how would you make it more balanced? Well, one thing you might do is to add some things on the top that would correspond to the things on the other side. It's a little bit more balanced. Not completely, so let me continue. Now the top is balanced, right? But you look at the bottom part, it's still not balanced, so let me add a few more things. It's now balanced. Welcome to the world of supersymmetry. Because you see, supersymmetry, this isn't the balance itself isn't the reason why we physicists think this. There are other deeper reasons. But this is the simplest way to understand what supersymmetry is. What it does, let's go back to the original, what it does is balance the particles that we've seen. What we've seen here are the things in the standard model. By adding these other objects, we bring a kind of balance. The numbers of fermions and the numbers of bosons in the supersymmetric model is the same number. That's the balance we're talking about. Now, supersymmetry may not be an attribute of our world. It's mathematics. When I was a graduate student at MIT, I was the first person at the Center for Theoretical Physics who got really interested in supersymmetry, and I was running around like a young person with their head on fire trying to find an advisor. And I couldn't find anyone who actually knew anything about it, so I wound up doing the thesis on my own. In my entire career, people like me have been looking for this stuff. We don't know that it's here, and in fact, I was very interested in a set of transparencies that Tara showed, talking about the supersymmetric searches that have been underway in the first run at the LHC. And if you look, that's a pretty impressive list of negatives. Now, there are a lot of people who, as Tara mentioned in her presentation, said, why are you betting on this dead horse? Maybe it is wrong. But by the same token, as mentioned in the presentation, what we call the parameter space of supersymmetric models is enormous. So enormous that we can't be completely sure that we've checked every place that it would occur. I like to tell people, it's like if someone said, why don't you go look for one of the giant redwoods and you go, let's say, to Florida. You're probably not going to find any giant redwoods there, right? You're going to find them if you look in the right place. Supersymmetry kind of has that flavor to it, although it's getting more and more difficult for it to hide. So people like me have been studying this, for me, my entire professional life. I still don't know if it's right or wrong. It's now been 30 years or so, almost 30 years. I'm hoping that it's right. I don't know that it is. But for me, the more important thing has been that this is what science is all about. You see, in science, you make a commitment because you're actually optimistic about our species. You give your best to find something that you hope will be important. And one of the ways I explain to people why it's important, and I said this to a group of students yesterday, I say, go outside, do you see any dinosaurs? And everybody says, no, no dinosaurs. And I said, maybe one of the reasons is there were no dinosaur scientists. You see, when the environment changes drastically and challenges the existence of a species, the only tool that I can see that we have to defend ourselves with will be our technology. That technology, in turn, is grounded in our science. And so, in fact, one of the things that scientists are doing is to making an attempt that when those challenges come, and they're going to come, I mean, people don't realize, for example, that dinosaurs were the dominant species on this planet for about 200 million years, if I remember my ancient history. That's a long time. Humans, 1 million or 2 at most, right? And so if the dinosaurs could be wiped out by a change of environment, what makes us think we're so special? I don't think the universe works like that. And that's why we have to invest in our science. And that's why this conference is important, because it gave some of my generation's greatest scientists the opportunity to talk to people who are not scientists and describe some of the advances that we have made. Thank you.
Thank you, Professor Gates. At this point, I think he has time for a couple questions, if anyone has any. I thought Lawrence would be right up there.
Well, one of my heroes was a gentleman by the name of Richard Feynman. And Richard Feynman had lots of rules, and one of them is to know when to say, I don't know. He was very skeptical of experts. I am not an exobiologist, so I am the last person in the world to be able to answer questions about life on other planets. However, I will say that with the kind of work where the number of exoplanets is increasing, it increases the chances that life is out there, but that's as far as I can go in good conscience. Locally, you can always ensure that you get a collapse. If you put a sufficient amount of matter in a sufficiently compact volume, you're going to get some kind of collapse. On the other hand, in order to get the kind of expansion that George talked about and also Lawrence talked about, you actually have to have a sufficient volume where you can pack in dark energy, because that's what's driving the expansion. So yes, dark energy is actually here with us, which also means that yes, we are getting expansions, but the amount is not sufficient to drive the kind of devastating effect that is essentially described at the end of the universe. Yes, dark energy, we believe, is everywhere, but you have to have large volumes of it to really drive these voids.
Looks like we have one more question back here.
Associated with that, we expect
No, in fact, no. In fact, and again, I'll defer to Lawrence because he actually very poetically showed us sort of the end of the universe in his talk today. No, in fact, eventually, if one waits long enough, the expansion, in fact, shuts down all sorts of energy sources. The universe winds up a cold, dark, lonely place.
Well,
That's the good news.
It's-
That's the good news.
what a depressing thought to end this conference on. Let's thank Professor Gates one more time.
Thank you for being part of Nobel Conference 49. Thank you for your support of Gustavus Adolphus